Here is a direction nobody talks about. We have sent spacecraft to every planet in the solar system. A probe is rolling across Martian dust at this very moment. We have dropped instruments through the cloud layers of Saturn and brought back close-up photographs of Pluto's nitrogen glaciers from less than 8,000 miles out. Crossing billions of miles of open space has become almost ordinary. But one direction has stayed almost completely untouched, a direction that sounds like the simplest possible destination and turns out to demand more energy than almost any journey we have ever attempted. That direction is straight up, perpendicular to the flat disk where every planet orbits, directly above the North Pole of the Sun or directly below the South Pole. The vertical exit from our solar system. It sounds trivial. You point the rocket up and fire. The problem is that the physics of our solar system will not allow it, not easily, not cheaply, and possibly not at all without a manoeuvre so counterintuitive it sounds like a mistake. What follows is the full picture. Why vertical escape is harder than reaching Pluto, what waits above and below the solar poles if we ever get there, and the strange, almost reckless manoeuvre that scientists believe might be the only real way out. Start with a number that changes everything, 30 kilometers per second. That is how fast Earth is moving right now, sideways, looping around the Sun on its annual orbital path. Not 30 kilometers per hour, not per minute, per second. Every single second, the ground beneath your feet is moving sideways through space at roughly 67,000 miles per hour. This velocity is not optional. It is not something you can turn off. It is baked into the physics of how Earth formed 4.5 billion years ago from a spinning disk of gas and dust that handed its angular momentum down to every planet in the system. Everything in our solar system orbits in roughly the same flat plane because everything came from that same spinning disk. The planets, the asteroids, the comets, the dust, all of it is locked into a shared motion, going sideways around the Sun in a giant flat ring. When a rocket launches from Earth, it inherits that motion instantly. A spacecraft sitting on a launch pad is already travelling at 30 kilometers per second. Mission planners use this as a gift. To reach Mars, you just need a small adjustment to what you already have. A few extra kilometers per second in the right direction, and the existing sideways motion carries you across to another world in the same plane. But what happens when you want to go perpendicular? When you want to leave the plane entirely and travel directly above or below it? Now that sideways velocity is no longer a gift, now it is a wall. To travel vertically out of the solar plane, you first have to cancel the 30 kilometers per second you already have. Then you have to add enough new velocity to actually climb. Engineers describe this in terms of delta 5, the total velocity change a spacecraft must produce using its own engines. Sending a probe to Mars requires roughly 4 kilometers per second of delta V from Earth orbit. Escaping straight up out of the solar plane requires approximately 30 kilometers per second. That is not a rounding error. That is nearly 10 times as much energy. Reaching a point just a few million miles directly above the Sun's North Pole would cost more fuel and more rocket performance than reaching Pluto 3.5 billion miles away in the same plane. This is the trap. The orbital speed that makes reaching other planets almost effortless is exactly what makes leaving the plane brutally expensive. We can hop between worlds in the same ring of orbits because we are already moving in that direction. But the moment we try to go vertical, we are fighting 4.6 billion years of accumulated sideways momentum all at once. Because this vertical escape is so expensive, almost no spacecraft has ever attempted it, which means what lies directly above and below the Sun is still, in 2026, almost entirely unknown. Think about what has been explored and what has not. We have high-resolution terrain maps of Mars. We have watched geysers erupt on Enceladus. We have seen the heart-shaped nitrogen plain on Pluto and the braided rings of Saturn. We have photographs of the nuclei of comets from distances of a few kilometres. We have radar maps of the surface of Venus through its cloud cover. But the poles of our own Sun, the star that keeps every one of us alive, have barely been observed. The closest star in the galaxy, 100 times wider than Earth, and two of its most important regions have barely been photographed. The reason this matters is not just about seeing something new. The polar regions of the Sun are where the most consequential solar activity is generated. The fastest solar wind, the stream of charged particles that constantly blows outward through the solar system, originates from open magnetic structures above the poles called coronal holes. The magnetic field of the Sun reverses polarity on an 11-year cycle, and the process that drives that reversal is rooted in polar dynamics. Space weather, the radiation environment that affects satellites, power grids, and any future human presence beyond Earth, is shaped by what happens at the top and bottom of our star. Yet we have been observing all of this almost entirely from the side. Like trying to understand the behaviour of a hurricane by observing it only from the horizon. Only 2 missions have ever broken even partially free of the solar equatorial plane. The first was Ulysses, a joint NASA and European Space Agency spacecraft launched in 1990. To reach any polar inclination at all, Ulysses had to travel all the way out to Jupiter and use the gas giant's enormous gravity as a slingshot, bending its trajectory almost 80 degrees out of the ecliptic plane. From that tilted orbit, falling back inward toward the Sun, Ulysses made the first in situ measurements of the fast solar wind flowing out of the polar coronal holes. But the spacecraft carried 1980s instrumentation and no camera capable of imaging the solar surface from above. It measured the environment without ever seeing what was there. The second mission is Solar Orbiter, a European Space Agency probe launched in 2020 and currently using repeated gravity assists from Venus to tilt its orbit gradually. In early 2025, Solar Orbiter returned the first direct images ever taken of the Sun's south pole. The photographs show a magnetically chaotic region of tangled field lines and dynamic plasma structures, fundamentally different from the calmer solar surface visible from Earth's viewing angle. Until last year, no instrument built by human hands had ever seen the top or bottom of our Sun. Not once. Not clearly. There is a second mystery that vertical escape could solve, and it concerns the shape of the neighbourhood we live in. Surrounding the entire solar system is a structure called the heliosphere, an enormous magnetised bubble generated by the solar wind. This bubble inflates outward in all directions, pushing back against the flow of interstellar gas and particles that move through the galaxy between star systems. Everything we have ever sent into space, every satellite, every probe, every spacecraft, has travelled within this bubble. The Voyager probes became the first human-made objects to cross its outer boundary in the 2010s. For decades, astronomers assumed the heliosphere was shaped like a comet travelling through the galaxy, a rounded nose pressed against the incoming interstellar wind, and a long tail stretching out behind. This was the standard model, reproduced in textbooks and visualizations for generations. In 2020, a research team working with new NASA data proposed a completely different shape. According to their model, the heliosphere more closely resembles a deflated croissant, a rounded central structure with 2 curved jets extending from it and no long trailing tail. The 2 models predict different particle environments, different boundary conditions, and different interactions with the interstellar medium outside. The reason we cannot resolve this debate definitively is that every probe ever launched has measured the heliosphere from within the plane of the planets. The Voyager spacecraft crossed the outer boundary almost horizontally, useful but limited in viewing angle. The same way trying to determine the shape of a building by walking around its base tells you less than looking down from a helicopter. A spacecraft travelling straight up out of the solar system, gaining altitude above the ecliptic plane and looking back at the heliosphere from outside and above, would be able to answer this question directly. We have never had that vantage point. We do not even know what our own bubble actually looks like from outside it. So how do you solve the vertical problem if bigger rockets are not the answer? The approach generating the most serious attention in astrodynamic circles involves doing exactly the opposite of what intuition suggests. Instead of climbing, you fall first. The concept is called the solar O-berth maneuver. A spacecraft using this technique does not immediately try to escape the solar plane. Instead, it deliberately dives inward, falling toward the Sun under gravity, accelerating continuously as it descends. At the closest point of the dive, called perihelion, the spacecraft may be moving at over 100 kilometers per second relative to the Sun, many times faster than any probe has ever travelled. At precisely that moment, the engines fire. This is the counterintuitive part. The same amount of propellant that would produce a modest velocity change in deep space produces a dramatically larger change in orbital energy when burned at high velocity deep inside a gravitational well. This effect, described by the physicist Hermann Oberth in 1929, means that a perihelion burn near the Sun is worth many times what the same burn would be worth anywhere else in the orbit. The dive turns the Sun's gravity into a force multiplier for the engines. After this maneuver, the spacecraft exits the inner solar system on a trajectory tilted sharply out of the ecliptic plane. What was impossible with a direct climb becomes achievable by falling first. Solar sails add a second path. A reflective membrane tens of thousands of square meters in area, unfurled in space, can use the continuous pressure of sunlight itself to slowly tilt an orbit over months and years. No propellant consumed, no engines fired, just photon pressure pressing on a thin metallic film, gradually walking the spacecraft's trajectory out of the plane. Hybrid mission designs now combine both approaches. Imagine a solar sail spiraling a spacecraft closer to the Sun, reaching high solar wind pressure and intense sunlight near perihelion, and then an O-berth engine burn at the closest point. The result is a probe that reaches the polar regions of the Sun, or escapes entirely above the ecliptic disk, on an energy budget that neither approach could achieve alone. If a spacecraft ever makes this journey and reaches a position directly above the Sun, what does it actually encounter? The solar system from above is a disk. All the planets, their moons, the asteroid belt, the scattered dust, all of it compressed into a flat ring around the Sun. A camera pointed downward from above the solar North Pole would capture an image no human being or machine has ever produced. The solar system as a whole object, seen from outside its plane, arranged like a thin coin against the backdrop of the galaxy. Above the ecliptic plane, the environment also changes. Within the disk, billions of years of comet fragments and asteroid collisions have left a thin haze of dust. On very dark nights on Earth, this dust is visible just after sunset as a faint column of scattered light rising from the horizon, the zodiacal light, sunlight bouncing off particles in our local plane. A spacecraft climbing above this dust layer would emerge into a dramatically cleaner optical environment, useful for instruments trying to detect faint signals that are currently washed out by foreground scattering. Above the solar equatorial regions, the turbulent slow solar wind gives way to the fast solar wind streaming from the polar coronal holes, particles moving at 700 to 800 kilometers per second in a thinner, steadier flow. A different radiation environment with different implications for spacecraft longevity and for the physics a probe could study. And if the spacecraft keeps climbing, eventually it would cross the boundary of the heliosphere and look back at the bubble from outside. We would see the real shape of our home in the galaxy, the structure that has been shielding us from interstellar radiation since before Earth existed, finally visible as a whole object for the first time. We have mapped the ocean floors. We have photographed the far side of the moon. We have sent cameras past the edge of the solar system. The view directly above our own star still does not exist. The photograph, looking down at our solar system from outside its plane, has never been taken. That is the journey nobody has made yet, and it is closer to possible right now than it has ever been.